Hi everyone, my name is Sergio Marquez. I work for OneSpin Solution. I'm a field application engineer based in UK. So I live in Bristol. I gave this presentation 2 days ago in Reading, then I flew over. So I'm going to talk about integration verification using formal. Before I go into that, a quick slide on OneSpin. OneSpin came basically from a spin-off from Infineon Technologies. So it was development that started actually already in Siemens and then in Infineon, and then it was spun off as a company a few years ago. So the focus of OneSpin products at the moment is, so we have products for automated solutions. So we saw in the presentation before from mentors. Oh, sorry. We saw in thanks. Maybe here. Thank you. That formula is growing. I don't remember, the figure was 40% or something. So we see this more and more acceptance of formal, which is a good thing for us. And part of this is certainly driven by more and more solutions available that tackle specific problems that are push button. They do not require special knowledge, and so that everyone can pretty much apply them, designers or verification engineers. And this is certainly part of the story, part of the success of formal verification. I'm talking about logical connectivity, X-propagation verification. I'm talking about verification IPs, all nice prepackaged things that people can just use out of the box, push button, and really, you don't need the formal expert basically. Another important point where we see a lot of interest is coverage. So the question comes often, okay, I have these assertions. How can I need to do, fill my coverage matrix, and I have all my test bench, and I get to this point, and really, I have some assertion here which really are covering this area, but how do I integrate this matrix with the simulation matrix? And here we have a product which is called Quantify that really derives effectively coverage information out of assertion. It's again push button. You have someone has written assertion, of course. You run this tool push button, and you get coverage matrix that you can also export in XML format to be integrated with simulation matrix. We currently have statement and branch, and obviously there is more to do, expression coverage, toggle coverage, And we also have the equivalency checking product. We are also in the FPGA market there. We are actually leader in the FPGA market also because we are the only one that can really do equivalency checking at FPGA. Because this relies to do equivalency checking for FPGA that use advanced optimization. You need really strong technology that does sequential equivalency checking, and actually we do partner with major FPGA vendors. All this technology, from the automated solution, the assertion coverage driven, to also the FPGA, they all rely on the same foundation technology. So what I'm going to talk now after this introduction is a specific use case. So I'm going to dive into a specific case that we developed with our customer Renesas. So actually I want to thank Renesas and our team in Japan for coming up with this and sharing this with us. It's an interesting application in the area of something that Jerome touched before. How do you leverage IP work at the SoC level? Like things that you can ship along the IP that then can make the SoC integration easier. This is, let's say, it's not the full answer to that, but it is a point that actually brought a lot of improvement for this specific problem at Renesas. So Renesas they have an MCU platform development, and they basically have develop a base product, and then they develop a lot of variations of this product by using different IPs, different peripherals, and different parameters for the same IP, so a different instantiation of the IP. And they obviously, the goal of this is to have a large variety of differentiated products that target specific things, but being able to very quickly develop this. So, I mean, you can obviously, just to give an idea of things that can change, you can change memory sizes, you can have different selection of port and packages, different selection of IPs, bus bridges. And the problem was that, in a sense, they didn't get the verification productivity that they were expecting by this. Because, I say, okay, we are just changing a couple of IPs here, and, but they still needed to do a lot of work for verification. So verification was a challenge. So really, we have two different challenges here. So obviously, you want to have your IPs properly verified. You want to be able to reuse your verification. You have a new instance of your IP. You are using different parameters. You want to have high-quality verification. Then on the SoC level, you're going to have to check logical connectivity. You want to check, obviously, communication channels, all the various paths between master and slaves. We have seen quite a lot of these. And what they had really was, pretty much a specific test bench. To achieve the high coverage they wanted, they had to quite, adjust the test bench each time and write a lot of directed test scenarios. And this was quite time-consuming. High-level slide on actual numbers, what it means time-consuming. I have some numbers later on. Okay, so they did develop some assertions for their IPs. So when they put these IPs in a library, and then let's say another group uses. So when they were shipping the IP, they shipped also some assertions with them that also were used to do IP level verification. And we will have a look at this. So how these assertions were looking like. So OneSpin has a SVA library, system verilog library, that enables users to write assertion into a higher level, so interface level. So you can see there a timing diagram and the corresponding assertion that is derived. This is SVA. And by the way, who has ever written an assertion here? Is there anyone who actually written? Okay, good. That's quite a lot actually. Also, have you run this assertion in formal and simulation or only simulation? Formal? Okay, so there are less, so some people only do it for simulation. Okay, good. So the key point, one of the key points of this methodology is to be able to easily translate kind of the timing diagrams you can have in a spec with describing a certain interface transaction into a property. At this point, the important thing I want you to notice is that there is a clear separation in the style of assertion between cause and effects. So you set up kind of your scenario and then implies what are you going to verify. Okay, so this is an important point that will become, also important for the next thing. So this kind of assertion, they were shipped along the IP. Now, the question is, hey, but can I use this assertion to do IP integration verification? By the way, just to be clear, this goes beyond the connectivity check. It's not just a wiring check. You want to really make sure that if a certain IP raises an interrupt, can, under each operating condition of any other IP, is this going to, for instance, reach the CPU, being properly taken by the CPU? So it's a functional connectivity. It's really looking at the communication between, in this case, the CPU and the IP that is raising the interrupt. So if you actually want to verify this for any possible combination, if you have a number of IPs, and you want to check, for instance, you're looking at the IPC communicating, let's say, with the CPU, that's your target. You want to make sure things go well if in the other IPs there's nothing going on, or if there are operations going on with IP B but not IP A. You know, if you really want to make sure this communication channel works correctly for any other possible condition that's going on in the system, it's basically impossible to do with simulation to start with. Or, you know, if you want to get good coverage, you need to write a lot of different scenarios that cover, that control each and every IP in the test. And, you know, you can already start thinking it's not easy. Okay, so traditionally what they did was simulation. So they had to adjust their test bench, and they had to, you know, even if the IP were reused, they had to work out all these new scenarios that they had to check. So even as basically the point is, even a simple change into the system, if you change a couple of IPs, would require a lot of work to them. So the idea was, okay, we have some transaction level assertions for the various IPs, and we have also, you know, for our, let's say, PF module, what they call PF module, CPU, DMA, and which is typically, let's say, the core of their product. So how can we reuse them? So in the specific case I'm looking is the interrupt controller, but they did this also to check connectivity between master and slaves, according, you know, to how master and slaves are supposed to communicate, if they are supposed to communicate. So they have, in a schematic you know, view, they have, for instance, in this case, some source of interrupt, and we have some assertion that describe the interrupt interface here. We have some connection IP with some assertion again. We have a destination IP, for instance, the CPU, with some assertion again looking at the interrupt interface. So what they did is basically they take pieces of this assertion and recombine them to create an assertion that talks about the SOC. So the way we saw the style of assertion that was separating cause and effect enabled them to take the cause of an assertion developed for IPA, the cause of an assertion developed for the connectivity bit, and maybe the expectation for an assertion developed for the CPU, put them together and have a new assertion. So here you see this assertion was developed for one module, this for another module, this for another module. They are developed with these styles. Something implies something else. And then they take pieces of this and they build somewhat automatically a new assertion that is looking at SOC level functionality, and then can be used to verify functional connectivity at SOC level. And I hope you find this half as interesting as I found it, because I think it's really cool. I didn't do it, the guys in Japan did it. So this is how the, let's say, combined assertion looks like. And yeah, this is also very interesting, because as I promised, there are some numbers. And the specific case of the interrupt controller, they had 130,000 lines of code for the simulation test bench. Obviously, much of this was automatically generated, but nevertheless, they had 41 days of effort. So they actually, for this specific case, they made a clear head-to-head comparison. So these are Renesas numbers. And they had the fairly high runtime, roughly an hour per test, 447 hours. With our with the formal approach, they spent 4.5 days, because bear in mind that we are not talking about here about having to fully formally verify the IP. You might just have the few assertions that describe the interrupt interface in this case. So that's enough. You don't have to have the full formal verification to reuse it. And they had much less code generated, like an order of magnitude less. And then looking at one interrupt sources at the time, they had the runtime of 9 hours. And looking at a possible combination, they had 547 sources of interrupt. They had the runtime of 73 hours, which is still, it's a sizable runtime, but still it's much less than the simulation runtime, and it provides a much more quality because you're looking at all possible combination. So this is, I think, a very, very interesting result. I think another interesting aspect of this is that, often when you do formal verification, you think it's great, it improves quality, it improves quality, but it's not clear to see what kind of a simulation effort can I safely replace with the formalized effort. Because obviously there are going to be some overlaps there, and you want to minimize overlaps. If I've done this thing with formal, I improve the quality, but I can actually get rid of some simulation tasks. And in this case, it was actually a great example because this was exactly a task that could be replaced, cleanly replaced by this different approach. And I think this is also important to highlight. So in summary, we saw, a little bit verification of the IP blocks, this kind of transaction level assertions. And we saw how these assertions that are shipped along the IP could be leveraged for SOC integration verification, and provides higher quality and also savings in time, runtime, and human time of almost an order of magnitude. So yes, that's conclude my presentation. I hope you found this use case interesting. And any questions?
Any question? The webinar is on.
José Manger, Attesti, microeconomics. You mentioned about combining assertions which were developed at IP level into some SOC level assertions. I might have missed the point, but is that done automatically with the tool, or is it something to do by hand?
So we do not have a fully push-button automated solution at this point, but if you look at the effort, you can say that it's either automated, it's very easy. It is actually very easy because, so it is a point that should be automated, but actually you're literally taking pieces of assertion and putting them together. So it's a very, in fact, the Renesas has some script. I mean, I cannot say that OneSpin is a product for this at the moment, but for instance, Renesas did this with scripts.
Simone Borri, Abilis Systems. So Sergio, it seems that you highlighted at the beginning of your presentation that today your focus of formal verification engines is more to provide out-of-the-box solution to some specific problems. So does this mean that the good old way of using the formal engine to verify a certain property, where you write the property and this is something which is not really the focus today? And to this question then, has there been any improvement in the way the tool can handle this kind of situation where you want to prove a certain design property? What is the kind of design size and sequential depth which can be handled by the tool today?
Okay, so the point of automated solution is really to get more users to use the tool and to quickly solve specific problems. On actually writing assertion, we are very focused on that. And we have, for instance, this quantify tool that reads the assertion and pops coverage out of the assertion that you have written. And in terms of the capacity of the tool, you can see, I just got an example of SOC level assertions. So the capacity, of the tool to handle complex design and complex assertion has grown dramatically in the last years. And the bottleneck there at this point is not so much the technology, but is about users being able to capture complex functionality within assertions. So it's not actually anymore a technology bottleneck, it's a user bottleneck, and that's why we have automated solution. And also we have this kind of layer on top of SVA, which is you know, you can write anything you want in SVA, but you need some kind of layer that kind of force you to write something in a cleaner way. And we have the library for that. And we saw also how this, for instance, then enables some further reuse of the assertion at SOC level. Does this answer the question?
Thank you. Okay, thank you. Giorgio, do you want to say?